Welcome everyone to the Chapter 5 vodcast. In this particular vodcast, we're going to cover some of these topics, including energy, how heat and work are related, calorimetry, enthalpy, Hess's law, and something called enthalpies of formation. All right, you guys, lots of stuff to cover, so let's dive right in. Make sure you have your guided notes in your textbook with you. So the first thing that we need to review is the concept of temperature. And the thing that you guys need to realize is that when we stick a thermometer into a substance, we're taking a measurement of how fast the particles are moving. That's sometimes known as kinetic energy. Kinetic energy is the energy of motion. So when you stick a thermometer into a substance and you're getting that temperature, you're really actually taking a measurement of the average motion of all the particles in the sample. Because let's say something has a temperature of, say, 70 degrees Celsius. That's pretty hot. But you're going to have some particles that are moving a little bit slower and some particles that are moving a little bit faster. So when you take a thermometer and you're taking a measurement, it is the average motion of all the particles in there. So here is a graphical interpretation of exactly what the particles are doing at some various temperatures. So this is called the Maxwell-Boltzmann distribution. And it is a graphical representation of the motion of all the particles in one particular sample. So here, with the yellow, take a look at that yellow. If we come straight down right here, this is kind of like where the average motion of most of the particles are. So if you stuck a thermometer into this particular sample, that thermometer would have a reading that would represent the average, or where most of the particles are moving. The temperature would represent where most of the particles are moving. But if you increase the temperature of the substance is going to record at a higher temperature. Now we're going to have kind of like a stretching effect. And something that you should notice on this graph is that when we have zero energy, we're going to have zero particles at zero energy because particles have to have energy. But anyway, when you come down here, we're at a slightly higher temperature, and so the temperature on the thermometer is going to increase. You should notice that even way out on the far right-hand side of this graph, you'll notice that the end result is that these particles are moving even faster, even way out here at the higher end. Let's take a look at that red. Let's really crank up the heat. So when you really crank up the heat and you crank the temperature of those particles, you'll notice that the average does move a little bit further out right here, and so you have a wider distribution. You see, the area that is underneath each of these curves represents the number of particles in that sample and exactly how much energy each one of those particles has in the sample. So if I were to shade in this area for the yellow, we would have some particles in that sample that are moving at an extremely high rate of speed on the high side over here. Okay, but there's not very many of those particles. Looks like most of the particles, if we took, this chunk right here, most of the particles are moving with this amount of energy. But you still have some particles that are moving a little bit slower and some particles that are moving a little bit faster still. This concept of energy and the motion of particles is kind of the grassroots concept of thermochemistry. So in this particular image, what I tried to depict on the left side is an object that is hot. And this object has these little packets of energy inside of it. And you'll notice that the object on the right has less packets of energy. Now, if we were to touch these two objects together, if we were to bring them in contact with one another, the object on the left would transfer some of those packets of energy to the object on the right. This is kind of one of those things that we just inherently know. Like if I showed you a hot pot of water and it was boiling, you wouldn't necessarily want to stick your hand in there. If you did stick your hand in there, well, the energy from the hot boiling water would transfer to your hand and it would hurt because it's transferring energy to your hand. You see, energy has a tendency to want to travel from areas of high concentration to areas of low concentration until we reach a very important part. That very important balancing of energy is sometimes called thermal equilibrium, in which both of these objects would establish kind of like the same amount of energy. This movement of energy from the hot object to the cooler object, it is a transfer of energy that we call heat or thermal energy. And this thermal energy is given the symbol Q. But see, that's not the only way that we can transfer energy from one system to another. You see, there are other ways to transfer energy from one system to another, other than just heat transfer. These include mechanical energy transfer, electrical, light, or even chemical energy. These are all considered energy in the form of work. You see, when you bring two systems together, they can do work on one another. But the only calculations for work that we care about are volume changes, which is a type of mechanical energy transfer. And I have a great example for you. And this example comes from one of my favorite people, from Bozeman Science.
And a great example of that is in a four-stroke engine, so in an internal combustion engine. So if we start at plane, what really is going on is that we're taking in gasoline and air into a combustion chamber. There's an explosion which drives the piston down, turns a crankshaft. We're also getting rid of that exhaust. And what it's really doing is transferring the energy in that gasoline into mechanical energy of the movement of your car. Now we lose a lot of that energy to heat.
This work energy can best be described as basically a force that is exerted over a specific amount of distance. So now we have two different ideas of this energy that we're going to focus on. One of them deals with heat transfer, and the other one deals with work transfer. But an important concept to remember is that in all energy, in any form, it can be converted from one form to another, from heat to work to electrical. You know, if you think about it like a solar panel, it can collect that light energy from the sun and convert it to electrical energy, and we can connect that electrical energy to a hot plate. You see where I'm going with this? We can convert energy from one form to another, but the total amount of energy cannot be created nor destroyed, just transferred from one form to another. And that, ladies and gentlemen, is the first law of thermodynamics. So the total amount of energy that a system has will be calculated by taking the work energy and the heat energy and adding them together. So if heat goes into a system, sometimes we call that an endothermic process. But when heat is released from the system, we call that an exothermic process. So the value that we give to the Q and to the W, Q is heat, W is work. The value, it can either be positive or negative. If the value is positive, that means that we have an endothermic process. That means that heat is going in. Endo, right, means in. Thermic. Therm means heat. But if heat is taken away, well then the value of your Q is going to be negative. And that would mean that that is an exothermic. That exo means out or being removed, and therm means heat. So W, or work, can also be positive or negative. If work is being done on to the system, then from the surroundings, means the surroundings is pushing into the system. That means work is being done on the system, and it would be a positive value. But when work is released by the system, in other words, the work is being transferred from the system to the surroundings, well then the W value would become negative. So the overall value of the energy of the system is sometimes given the symbol of E. And this E for us is going to include both heat and work. Some specifics about the symbol delta. Anytime you see the symbol delta, that means change in. So the change in the overall amount of energy that a system has is found by taking the final total amount of energy that the system has and subtracting it from its initial. Now, if your delta T is positive, that means that the overall final energy is greater than the initial energy. That would be an endothermic process, because the final process, the final system has more energy than how it started. So that would be an endothermic process, or an energy being added to the system. But if we have an overall exothermic process, that would mean that the initial would be a greater amount of overall energy than the final. So the concept of enthalpy is given a symbol of H, okay? And really all you need to see is that enthalpy is the culmination of the heat flow in a chemical reaction with the work being done in the volume or pressure changes. And chemists have many tools to their use to help us figure out exactly how much heat was transferred from one object to another. And one of those tools that we have is a concept of specific heat capacity. Specific heat capacity is the amount of energy that would be needed to change 1 gram of any particular substance 1 degree Kelvin. And there's many different substances that have already been studied, and we already know what their specific heat capacity is. So here I have a few examples. This represents the amount of energy in joules that would be required to change the temperature of 1 gram of these substances 1 degree Kelvin. Now, some specific heat capacities are given in slightly different units. Like if you look at your textbook, they have molar heat capacity. That would be the amount of energy required to change a whole mole of that substance 1 degree Kelvin. Now there's a very important unit conversion that I think you might want to jot down. Frequently in some of these AP exams, they may ask for the unit of energy to be represented in joules. But every once in a while, you might get someone who wants the unit represented in calories. So down at the bottom here, you'll see that there is a conversion between calories and joules. Now, don't get confused, because sometimes we have others that even ask us for something a little bit more specific than just calories. They sometimes ask us for kilocalories. And there is a very subtle difference. So a calorie, lowercase cal, is different than a kilocalorie, which is a uppercase cal. Just know that an uppercase cal means kilocalorie. So what exactly would happen if I took all of these objects and I started to heat them up? If I put these all under a flame, these little energy packets will move from the heat source into the substance. Which object would heat up the fastest? You see, this object here, gold, has the lowest heat capacity. Once it absorbs just 0.126 joules of energy, it will increase 1 degree Kelvin. Which one of these will heat up the slowest? It looks like water can absorb a ton of energy before it changes its temperature even 1 degree Kelvin. Water can absorb over 4 joules before it experiences a temperature change. Therefore, it kind of makes sense that we use water to put out a fire. Gold happens to be a metal, and as you can see, we have another metal over here, aluminum. You'll notice that their heat capacities are fairly low. That makes sense because most metals are capable of transferring heat and electrical energy very quickly. So when you have an object that has a high amount of kinetic energy, it has all of these little energy packets. And when we take these larger objects, or these objects with a higher energy, and we put them, say, like into water, well, those energy packets are going to be released from the object that has a high kinetic energy, and those little energy packets are going to go into the water. Now, the reason why I'm bringing this up is because this is the root of calorimetry. We know what the specific heat of water is. So when it changes temperature, we can actually figure out exactly how many joules of energy have been released from these objects that have a higher kinetic energy. This is a very crude drawing of a calorimeter. Basically what you have is you have a chamber that is full of water. And inside of the chamber, we have a reaction vessel that is stuck on the inside. And a reaction will occur inside of this chamber. And when it does occur, you are going to have that energy being released from the reaction chamber into the water. And so little energy packets are going to be released into the water, which is going to cause that thermometer that we stick inside of the calorimeter to increase. Depending on how much energy is released by the reaction, that will change the thermometer a specific amount. Now, a calorimeter, a good calorimeter, has to be isolated from the outside world. So we have to have all of this insulation on the outside. Some essential information that we need to know is exactly how much water is inside the calorimeter, what is the initial temperature of the calorimeter's water, okay, and what is the final temperature of the calorimeter's water. So if you want to do a real simple example, let's pretend like the initial temperature of the water before a reaction is initiated inside the calorimeter is 50.0 degrees Celsius. And let's pretend that the final temperature after the reaction is completed is 75.0 degrees Celsius. Let's figure out exactly how much energy in joules was released by the reaction on the inside of the calorimeter. So we had 100 grams of water inside of the calorimeter. The initial temperature was 50 and the final temperature was 75. This piece of information up on top is the specific heat capacity of water, which has been studied many, many times, and we know that this is to be true. So all we have to do is figure out how many joules were released when we had a temperature change of 1 degree. So let's figure out exactly the temperature change that occurred. So as you can see, the temperature did go up. Sometimes the temperature is going to go down, which would indicate that the reaction has to absorb energy from the water. But in this case, it looks like the reaction released energy into the water and it caused the energy, the temperature of the water to increase. So to get the difference, you usually typically take the final temperature and subtract it from the initial. And in this case, that is a difference of 25.0 degrees Celsius. All right, we have the mass, which is 100 grams. Make sure that you are careful to observe the units that are being used in the specific heat. Sometimes it is per mole, but in this case we have per gram. So it looks like all we have to do is take the specific heat capacity, multiply it by 100 grams, and multiply it by the change in temperature. Now, something to also know is that when you do the change in temperature, the difference between those two, even though you see degrees Celsius right here, you can instantly change that into Kelvin because it's just the difference between the two values. All right, so basically on your calculators, take the 4.186, multiply it by the 100 grams, and then multiply it by the 25 degrees Kelvin. So this unit right here is joules per gram Kelvin. So if you look at how your units are canceling, the grams will be gone and the Kelvin will be gone, and you will be left with just joules. And I get 10,465 joules. I can also convert that into calories if I wanted to. So look back at the video, do a conversion between joules and calories, and tell me how many calories were released by this chemical reaction. So figuring out energy changes from heat release or absorption is pretty easy through calorimetry. The hard part is figuring out the amount of energy being transferred when the work is done in some kind of volume change, like mechanical energy changes. So with this one, here's a good picture. It's being taken from your textbook from page 176 and also from 174. Now work, when we have to do changes in energy, when it deals with work, there's a cool little formula, and it is W is equal to negative PV. So for us, we just want to make sure that you look at this little closer. It's called a closer look. It's on page 176 of your textbook. Let's dive in and take a look. All right, so if we come back to this formula, let's take another look at this work piece. We've done a ton of stuff about heat, but let's kind of look a little bit closer at this work portion of enthalpy. What does that even look like? In this particular picture, what they have is they have a reaction that's releasing hydrogen gas. And so if you look at the initial position of the piston, it looks like it's at this level. But then in the final picture, because gas is being released in the reaction, it looks like the piston actually moved in an upwards direction. So let me be clear here. The reaction is doing work onto the environment. That means that the reaction itself is capable of pushing work out of the system. The energy is being taken away from the reaction. The reaction is pushing work out onto the environment. And so this would technically be, in this case, a negative value of W, of work. All right, because the work is being released by the chemical reaction. Now, if the environment was doing work on the system, the environment would be pushing down here on the piston would go downwards. And that would mean that work is being done onto the system. All right, so be careful. The value of W is very important. And you're probably wondering, when would a reaction ever cause the piston here to drop down? And there's a really good example of when the piston would drop down is when you have a change in the state of matter. If a gas is being compressed down into either a liquid or a solid, the overall volume of the system is going to decrease. And so if you have a decrease in volume, that means that the environment is doing work onto the system. But if you have an overall increase in the volume, that means the reaction vessel itself is expanding. And if the reaction vessel is expanding, that means that the system is going to do work onto the environment, which means it'll have a negative W value. So scientists have already done a lot of research on many, many different types of chemical reactions. And they've been able to tabulate the amount of energy either released or absorbed during those chemical reactions. So the thing that you have to be watchful of is what reaction do they provide you in the example. The reason why I mention this is because if you look at this reaction, it is balanced, but you should take note that it is producing 2 moles of water, and it is consuming, the reactant has 2 moles of hydrogen here and 1 mole of oxygen. So just make sure that you're taking good note of that, because this value right here is associated specifically with this particular chemical reaction, with the 2 moles of hydrogen, 1 mole of oxygen producing 2 moles of water. All right, now, second question is, what does this negative H tell you? Okay, the negative value right here, that's a negative value. What does that really mean? All right, well, you'll notice that you have this delta thing going on in the front. Do you guys remember what delta means? Delta is when you take the final, delta is when you take the energy of the final piece or the products and you subtract that from your initial or your reactants. So these right here are your products and these right here are your reactants. Okay, so a negative value would mean that your reactants actually have more energy than your products. So how could the reactants have more energy? Well, the reactants would have to release some kind of energy out into the environment in order for you to have a negative delta H. So remember, this would be an exothermic process. And an exothermic process means that the reactants are releasing energy. So a negative delta H means that you have an overall exiting of energy. So exothermic reaction. Okay, and that's true. Like, I don't know if you guys have ever seen The Martian, but hydrogen gas and oxygen gas, when they get together, they're highly explosive and they will produce water. And this particular chemical reaction is powerful enough that it can actually launch rockets into outer space. Here are some good rules to remember, so you may want to jot these down. Rule number 1 about enthalpy. Always remember that the value that they give you for delta H depends on the exact amount of the reactant that was consumed. So here's an example. How much heat is released when 10.5 grams of methane gas is burned at constant pressure? In order to solve this problem, you have to look at the information provided. In this chemical reaction that I gave you, sorry, the arrow is missing. In this chemical reaction that I gave you, it looks like the overall delta H is 890 kilojoules. Now, if you look at the reaction, you'll notice that there is no coefficient in front of the CH4. We can assume that this value that they gave you represents the amount of kilojoules that would be released during the burning of this compound per 1 mole. It's not given to you, but you need to realize that it is definitely assumed because you see the balanced reaction provided and you see that quantity given. So if you are given grams, you can easily change your grams to moles, and then for each mole, you are releasing 890 kilojoules. So in a stoichiometry setup, you would start with your 10.5 grams of the CH4. You would convert that mass into moles per 1 mole, right? Molar mass. And then using this information, you would say, all right, 1 mole of CH4 when it burns is going to release 890 kilojoules of energy. So 1 mole would release 890 kilojoules of energy. So I hope that gives you enough information to finish this problem by yourself. That will be on your guided notes. Enthalpy rule number 2. The enthalpy change for a reaction is equal in magnitude but opposite sign for the reverse reaction. So the way that this reaction is written from left to right is that CO2 and H2O will produce the CH4 and that O2. This is the same reaction that you just saw with methane burning in oxygen to make CO2 and H2O. But I reversed the reaction. Do you see what happened to the value of the delta H? It went from negative to positive. This does not naturally happen. You don't have like water and CO2 somehow magically forming CH4 and O2. So that positive value means that this is an endothermic process. This actually would require energy to be put into the system to somehow get that methane and that oxygen to come back. This would not happen very naturally. As a general rule of thumb, most exothermic processes happen spontaneously. Endothermic processes, well, they require work, So you got to put work in to make that reaction happen. Well, as kind of like a general rule of thumb in the entire universe, endothermic processes are a little bit harder to do. And the universe does not like to work very hard. All right, the last rule, rule number 3 about enthalpy. Enthalpy changes for a reaction depend on the state of matter that the reactants and the products are in. So a really good example comes from your textbook. Basically, if you have a combustion reaction and you're making water, is the water in the form of liquid H2O or gaseous H2O? Because that makes a crucial difference in the overall amount of energy that is either released or absorbed in a chemical reaction. So let's take this for example. If the product in a combustion of methane and some, in the other example that we just did, if it were gaseous H2O instead of liquid H2O, the delta H difference there would be negative 802 kilojoules instead of negative 890 kilojoules. So what is the difference between those two values? The difference between those two values is about 88 kilojoules. So in the textbook, they have you drawing these enthalpy diagrams. And I think this is probably one of the more important concepts that the AP chemistry test kind of wants you to understand. So let's see if we can do that together. Okay, The way that these energy diagrams typically work is you have enthalpy increasing from the bottom up. All right, so the only question that you need to ask yourself is, looking at the reaction, which one has more energy? Okay, so either the reactants have more energy or the products have more energy. Now, if you remember, this reaction is the burning of this CH4. Now, CH4 is burning. I hope you understand that is an exothermic process because heat is being released, right? It's being burned, and it's going to warm up the environment. It's kind of like if you stand back and you hold your hands out to a fire, you're going to feel the warmth approaching your hands. All right, so the chemical reaction is releasing energy. What that means is that your reactants have a lot of energy that is being burned and released out into the environment. So technically, your reactants should have more energy than your products. So I'm going to place the reactants up high because they have more energy than your products do. So I'm going to place the products down low. Now, the initial question was asking you, hey, what difference would it mean if you had a liquid H2O or a gas H2O being formed? Would there be a difference? And the answer is yes. And I think you guys probably know this already. Think about water. Which state of matter has more energy, more kinetic energy, more particle motion? Would that be the liquid or the gas? And you know that the gas is going to definitely have a little bit more energy than your liquid. So I am going to create a line that is a little above my original product. So I'm going to go in about right here, okay? And I am going to say that the products that are really down low on that white line, that would represent the products of the liquid H2O. Because I know that a gas has a little bit more kinetic energy. So this is the line, the yellow line would be if we had gaseous H2O being formed. All right, now what would be the overall differences? And these would be tabulated for you. But your initial chemical reaction, they gave you a value, right, a change of energy of approximately 890 kilojoules. That would be that particular change. And it is a negative because we are releasing that energy into the environment. So this arrow right here, the first arrow that I drew, would represent negative 890 kilojoules of energy. Now, what would this particular arrow be from here to here? All right, why don't we wait and just get a pause because we had some information that was given to us about the difference between water being a gas and water being a liquid. And that information was given just previously on the previous slide. This change right here, the yellow arrow that I just gave you, that would be a difference of approximately 88 kilojoules. So this is negative 88 kilojoules difference of energy. So if you wanted to figure out the delta E value or the enthalpy change when the products, instead of being a liquid H2O, now it's a gaseous H2O, you can actually just do the difference between 890 and 88. And that difference will give you negative 802 kilojoules of energy. So, states of matter in enthalpy reactions matter. So the last piece that we're going to check out right now is Hess's law. You see, there's so many reactions that we have tabulated over, chemistry history that we have enough information to get the overall energy of a reaction, either released or absorbed, just by looking at some tabulated values. Because you see, most chemical reactions happen in separate stages. And so if they happen in separate steps, we can use all of those steps, put them together to get the overall change in any chemical reaction. So Hess's law says that the overall delta H for a reaction will equal the sum of the enthalpy changes for each individual step. So Hess's law is not that bad when you just realize that this is kind of like algebra. you have to hit a specific target reaction. And you're given kind of like a table of all this other information that you guys have to go off of. So using the information provided, we can hit that target. So if you take a look specifically at what was given to you, you want to make sure that you have carbon solid over on the left. And it looks like in this piece, I've got carbon solid on the left. That's great. Now, on the product side, I want to see that carbon monoxide. Here's carbon monoxide, but you see how it's on the left? All right, so using some of the rules that I gave you for enthalpy, you can flip this reaction. But if you flip the reaction to make the products turn into the reactants, what has to happen to the overall sign here? That's right, if you flip the reaction, you also have to flip the sign of your H. So I'm going to go ahead and flip the reaction to say CO2 gas creates carbon monoxide gas and 1/2 oxygen gas. All right, cool. So I'm going to just kind of make sure that this goes away, and now I have changed my negative into a positive value. Okay? All right, so at this point, anything that appears on the left side and on the right side as the same state of matter and the same compound or element, you get to start cross-canceling stuff out. All right. So you'll notice that on the product side of the reaction, here I'm going to change colors. On the product side here, I've got carbon dioxide gas, but you'll notice I also have carbon dioxide gas here. This guy is on the products, this guy is on the reactants. Well, if they appear on opposite sides of that arrow, you get to cross them off. They cancel each other out, so these guys are gone. Okay, I don't see any carbon. You see how we've got carbon here? I don't see any carbon on the product side over here, so none of that's going to cancel. Your carbon's going to stay. The only other thing that I see that I can match up is the O2. All right. In the original one, you have one whole oxygen, O2 molecule, but on the product side of the other guy, you only have half. All right, well, you can actually cross-cancel halfies. So instead of having one oxygen, we now have a half oxygen left. So look carefully at what remains. At this point, we've got some carbon. This drops down. We have half of an oxygen left over. All right. The CO2 is gone, but look at the only thing left on the right side of the arrow on both of these is the carbon monoxide gas. So I've successfully crossed everything out. Now, to figure out the overall delta H of that, I'm going to take the negative 393.5 and I'm going to add 283.0. So make sure in your guided notes that you record that answer down. Okay, so while using the Hess's law, if you flip the reaction to make the products the reactants, you're going to have to flip the sign of H. But you can also, half, double, triple, or quadruple the reaction if you want. But if you do that, you're going to have to do the same thing to the value of that H. And here's a good example. Again, I love you, Bozeman.
You can see here that I have my NO on the left side, my nitrogen monoxide, and so that's good. I'm going to leave that there. But I really want is my oxygen all by itself on the left side here. So I'm going to take this and I'm going to turn this equation around. You can see that I got a negative value right here. So that helps out a little bit. You can see here that I have two ozones on the left side, and so if I could get those to cancel out, that's going to help me a little bit. So I could switch that around. So these are going to cancel, so that's good. What am I missing then? I got my nitrogen dioxide on the right side. Well, you can see here that I really want just one of these on the left side. And so what I could do is I could take that whole equation times a half. Well, if I take that whole equation times a half, what's going to happen to my delta H? I'm going to have to take that times a half as well. Okay, so let's see how we're doing so far. I got my ozones. I can get rid of those. Now if we get to the oxygen, this is really convenient. You'll find this is lots of times very convenient. On the right side now, I've got one O2 plus a half, so that's 3/2 of an O2, which is the same that I have on the left side. So I could cross out all my oxygens. Now I simply add that up. There's my target reaction, and now I simply add up all my delta H's, and that's going to be the overall exothermic reaction that I'm looking at. Okay, so did you learn qualitatively and quantitatively patterns in enthalpy of reaction. Again, it's simply a balancing act. We look at the energy it takes to break the reactants, the energy formed by the products, and whichever way that balance tips, it's going to tell us what kind of a reaction it is, and then we combine reactions to figure out the sum of all the parts. And I hope that was helpful.